Okay, next item on the agenda. We're still Unit 3, Work, Energy, and Power. Now, well, we've talked about systems. That was the first video. Second video, we talked about what work was and how to calculate it. In the next video, this video actually, we're going to talk about energy. So part 3 of Unit 3 is energy. So here are some learning targets. I know what energy is, I can calculate energy, and I know what the total mechanical energy is. So we're going to look at what energy is, how do we define it, how to calculate energy, or energies, I should say, it's plural, and you know what the total mechanical energy is. So first of all, let's talk about energy itself. What is energy? Again, this is another one of those words like work that has a bunch of different meanings to us in everyday life. If we think about the energy of, electricity, maybe think about energy as being hyperactive, the energy in the food that you eat, energy of gamma ray bursts or radiation, all kinds of things like that have words, or it can be described by this word energy. But energy, again, in physics is a very, very specific thing. Energy, for like a word style definition of what do you call it, qualitative, something that describes the quality of energy, is that energy is the ability to do work. So energy, and that's not really a great definition, but at the same time, it's a very good definition. But it's a scalar quantity, so it doesn't have direction to it. And in fact, when we talk about energy, it's never negative. You never have a negative energy, but you can have a negative change in energy. So that's when we have like a negative work results in a negative change in energy. Positive work results in a positive change in energy. But energy itself is a scalar, and so it is always a positive value. There is nothing in the universe that is energy. So it is not physical. What I mean by that is when we talk about velocity, there is physically a velocity happening. Time is passing and motion is happening. And so velocity is a real part of the universe. When we talk about forces, there are forces that can be explained in terms of subatomic particles that mediate these forces, whether it's a strong or weak nuclear force or gravity or whatever. But these forces actually exist in the world. You can measure them, you can see them, you can interact with them, you can change them. But energy is not something that really exists. It is purely mathematical. So purely mathematical. I know that a lot of times you've been told that, oh, a gamma ray is pure energy. It's not. It's really not. It's something else. What that something else is pretty complicated, but it is not what we would call pure energy. Energy itself is just a mathematical construct, and it comes because of the way that we do math and the way that we set up our coordinate systems. It's just this number that pops out when we do this special kind of math, and it happens to be super, super, super useful. And a lot of times I like to say that, yes, energy's effects can be seen, but it's not really doing anything. Energy is not really existing. What you're seeing is the effect of forces acting. You're seeing forces act over a distance. You're seeing work being done, but you're not seeing energy. It's not a real thing. So why do we use energy if it's not real, if it doesn't actually exist in the universe? Because it's easy to use, it doesn't have direction to it, it's easy to calculate, and it's easy to measure. And because of those reasons, we can use it and we can relate it to other things like forces or velocities or distances between two charged particles, something like that. So energy is super, super useful, super, super easy to do, does not really exist. However, in a lot of ways, you can think about a hammer. And a hammer does not exist in nature. There's nothing in nature that is a hammer. There are rocks, there are sticks, there are methods to fashion rocks to sticks, like vines and glues and things like that. But there's nothing that is a hammer in nature. We created a hammer as a tool to do something. And the similar thing with energy. We create energy, it's a tool to do something. And that something is to analyze a physical situation. So enough said about energy. I know I kind of went on a little rant about it. But the energy itself, the word energy, actually is related to work. So if we think about the word energy, it has Greek roots. It comes from the Greek word energia. So Energia. Or in Greek letters, it would be this. Epsilon, nu, epsilon, rho, gamma. Oh, that's another nu. So rho, gamma, and iota, and alpha. Energia, energy. So this word in Greek, well, in ancient Greek, it's actually a compound word. It's made from these two words, en, so en, or in English, in, like inside of, or not really inside of, but actually actively doing. And the other word that it's made up of is ergon, or in Greek, ergon. So this word ergon, or this means in, this word means work. And so literally energia is Greek for in work or at work or doing work or in action. So energy is basically something that involves work, maybe. A lot of times when we talk about a lot of different naming systems, we'll use like a Greek name for something and then a Latin or an English name for something else. And those two things will be very, very closely related. One of the classic examples I like to use when we talk about rotational motion, we've talked about position, we've talked about velocity, and we've talked about acceleration. When we go to talk about rotational motion, we'll talk about position, theta, we'll talk about velocity, omega, angular velocity, and we'll talk about angular acceleration, alpha. And so these are the Greek letters, these are the English or Latin letters, and they are analogous to one another. But that's not, that's another topic for another day. There are a ton of different types of energies, and any time that you have some sort of force or some sort of interaction going on or something moving, there's usually an energy associated with that. Some of the common types of energies that maybe you've heard of or have encountered in your everyday life are, let's see, there's thermal energy. So we know that maybe sounds familiar. We've heard of thermals, and we might think it's heat energy, and it is. Heat energy, thermal energy, heat energy is actually the end of the energy chain, right? Once you reach heat, you're done. You are never going to go back and do work once you're heat energy. So everything will eventually flow into heat energy, and once all the energy in the universe is heat energy, there is still conservation of energy. There's still energy there, but none of it can do anything. And so no more life is possible. The last protons will decay. And that's what we call the heat death of the universe. So at the end of time, like literally time won't be able to exist at this point. At the end of time, all energy will have been converted into heat energy or dissipated somehow. So the next type of energy we'll talk about is chemical energy. You're familiar with this energy, I'm sure, if you've taken chemistry, or if you ate breakfast this morning, you're probably familiar with it. This is the energy stored in chemical bonds. So maybe just a simple case, we talk about hydrogen bonded to hydrogen to make that H2 gas, that diatomic gas you learned about in chemistry in 10th grade, or that you learned about and you didn't pay attention to, or maybe just forgot. But there is a certain amount of energy in that bond. And if I were to break this bond, I would release heat or light or something like that, right? If you've ever seen hydrogen gas burn or explode, it burns, it releases lots of heat. There's a bang, a loud popping noise. And that's all energy being released from those chemical bonds, because what's going to happen is those hydrogens will reform with some oxygen and it will make H2O and energy. Well, energy will be released. So this chemical energy is energy from a chemical bond. But there's another type of energy that they talk about in chemistry a lot. It's nuclear energy. So this is the energy that we use to do nuclear power. This is the energy inside of a nucleus. We know that negative things like to repulse each other, and positive things do the same. They repulse each other. So if we have a bunch of positive things, they don't want to be near each other. A nucleus has tons of positive things all stuffed really, really close together, and there's a ton of energy in that. So when we fracture that, whether it's through like a neutron hitting a uranium atom, or whether it's through hydrogen fusing into helium, something like that, there's this energy exchange that happens there, and it's usually a great, great deal of energy for how small things are. So those are three types of energies. Let's keep going. There's some more. Energy type D, that's electrical energy. Electrical energy is the energy you think about when you think of energy from the wall socket, right? For power from the wall or electricity from the wall. This has to do with a charge separation. When I think about a wire, and there's all these little electrons, and they're moving down the line, right? One electron pushes into this electron, so it exerts a repulsive force and pushes that way, which pushes on the next electron, and so forth and so on until it goes down the line. But these electrons are going to move as they push on each other, and so what you have then is here's our first electron. It was here, so I'll do like a dashed outline. That's where it was, and it goes to here. So what's happening is now you've left an absence of a negative charge, and overall what an absence of a negative charge is a positive charge. Over here, we have that electron with its negative charge, and so now we have a separation of charges, and there's an energy associated with that. So when we are talking about separating charges, whether it's as it moves in creating a current, an electrical current, or whether it's just like a positive thing here and maybe a negative electron here, and the electrons maybe orbiting the nucleus, which is positively charged. There's some sort of interaction going on there as well, and so there's an energy associated with that. But this electrical energy has to do with charged particles being apart from each other, two negatives being close together, two positives being close together, or a negative and a positive being somewhere near each other so that they interact somehow. We also have a radiant energy. And this is when a lot of students ask me why energy isn't physical, because there's this radiant energy stuff. So radiant energy is the stuff that you see when we talk about X-rays, gamma rays, really, really energetic things that are released when we split nuclei of uranium, so nuclear bombs, stuff like that. But it's also visible light as well. Basically, any electromagnetic spectrum light. It could be your TV, the old TV broadcast signals. It could be your old radio signals. It could be visible light, infrared, ultraviolet. Anything in that visible light or in that electromagnetic spectrum is radiant energy, and it's not energy itself. It's not physically there. It's the result of moving charged particles or changes in a magnetic field that we're seeing, and not energy. So when we talk about a gamma ray burst being pure energy, it's actually a very, very, very intense change in a magnetic field or electrical field. But it is not a physical manifestation of energy in any way, shape, or form. Then, actually, let's do this in a different color. Then we'll have energy type F, which I'm going to call kinetic energy. You've probably heard of kinetic energy. It's been around for a long time, and you've probably heard of it back in grade school, middle school. But this is our energy of motion. Because you have mass and because you are moving, you have kinetic energy. We also have elastic, or what I will usually call spring potential energy. As the name suggests, this is the energy stored in a spring when it's compressed or stretched. And the last one that we'll talk about is this gravity potential energy. I do want to make a comment about gravity potential. Sorry, my writing's getting so sloppy. It's way at the bottom of the page. It's hard to keep it nice. I know it's never nice to begin with, so it just makes it so much worse. But gravity potential energy, I call this gravity potential energy. I give it the name E sub g. It is related to a force F sub g. But there's another type of gravity energy, which we call gravitational potential energy. These are the same energy. It's just that one is a special case of the other. So our gravity potential energy is gravitational potential energy just near the surface of the Earth. So when we're near Earth's surface, we can use this energy. And when we're far away, or two objects are very, very far away, or we're on a different planet and the mass is different or the radius is different, then we have to use this gravitational potential energy. But we'll talk more about that when we get to rotational motion stuff. So for now, we'll focus on this gravity potential energy, which is related to Fg, which, as we remember, is mass times gravity, g, the g constant. So that is kind of a brief introduction to gravity. At the risk of keeping this too long, I'm going to stop it here. But then we'll go deeper into these three energies I haven't read: the gravity potential, elastic or spring potential energies, and kinetic energy in the next video. So stay tuned for that, and we will see you later.